Hello everyone, my name is Gary O'Mealy, and in this video we are going to talk about the thyroid and its hormones. So the thyroid is one of the endocrine glands that we mentioned before that is under direct control by the hypothalamus and the anterior pituitary, the other ones being the adrenal cortex and the gonads. So anatomically speaking, the thyroid wraps itself around the trachea and also contains embedded on its posterior side 4 parathyroid glands that secrete hormone that aids in calcium regulation, but we will cover that in a separate lesson when we actually focus on calcium homeostasis. So you'll recall that the feedback axis for thyroid hormone regulation looks very much like this. The hypothalamus produces TRH, which stimulates the anterior pituitary to produce TSH. The TSH causes the thyroid to produce T3 and T4, and once a sufficient amount of T3 and T4 have been produced, then that hormone will feed back on both the hypothalamus and anterior pituitary and reduce their production of TRH and TSH. So in this video, we are going to look further into thyroid hormone itself, how it is produced, how it is regulated, and its effects on its target tissues, the things that we haven't really had a chance to talk about much yet. So if we look at the thyroid tissue histology here, thyroid tissue contains circular arrangements of cuboidal epithelia, and these structures are called follicles. You can actually see one here, and then you can see the nuclei belonging to the cuboidal epithelia on the edges there. So each follicle encapsulates a viscous fluid, think of a jelly-like fluid called colloid, and the colloid contains the raw materials and enzymes that are necessary for producing thyroid hormone. On the outside of the follicles, in the interstitial space, you find what are called parafollicular cells, or sometimes called C cells, and they produce a hormone called calcitonin, which also aids in calcium homeostasis, and we will discuss that in the same lesson that we talk about parathyroid hormone. So if we take a quick look at what a slice of thyroid tissue looks like, you can obviously see the follicular cells here. You see the colloid in the center of one of these follicles, the interstitial fluid out here in which you find the parafollicular cells, and then of course you're going to find capillaries spaced throughout, and this is going to be tried and true for every slice of endocrine tissue that you could ever look at. You're going to see a heavy infiltration of capillaries. It stands to reason that if, by definition, a hormone is secreted into the bloodstream, there needs to be places for that hormone to get into the bloodstream. So you will hopefully recall that thyroid hormones belong to the amine class of hormones, meaning that they are derived from amino acids, and amino acids are freely available to all cells, so cells shouldn't really have a hard time getting their hands on amino acids. But what makes thyroid hormone unique is that it also requires iodine atoms. So a major task that the thyroid and the follicular cells has to be up to is to collect and concentrate iodine from the blood and the extracellular fluid and then transport it into the colloid space. So if we're going to make thyroid hormone, we not only need the amino acids that we need, but we also need iodine as well. Notably, the thyroid is the only tissue in the body that actually needs iodine for anything. We don't get very much iodine from our diet, but we definitely need enough to supply the thyroid with enough to make its thyroid hormones. So let's quickly go through how thyroid hormone is synthesized. First, follicular cells regularly produce a large glycoprotein called thyroglobulin. This is, of course, not thyroid hormone. This is just a big old protein, and it is exported into the colloid space. Number 2, when TSH binds to its receptors that are on the membranes of the follicular cells, this activates the active transport of iodide, which is in its ionic form, from its low concentration in the extracellular fluid to its high concentration in the cytosol of the follicular cells. So, of course, this is an active transport process that requires energy. This iodide is then oxidized into molecular iodine by enzymes in the cytoplasm of these follicular cells, and then iodine, being a nonpolar entity, can then diffuse freely into the colloid space. So if you're keeping up so far, now we have thyroglobulin in the colloid, and now we have iodine in the colloid. The thyroglobulin is going to serve as the source of the tyrosine amino acids that we need in order to make our thyroid hormone. And then, of course, we have the iodine that we're going to need to use as well. The final step here is what is called organification reactions. These are catalyzed by peroxidase enzymes that are in the colloid, and they help to link iodine atoms to the tyrosines that are within the thyroglobulin. And then protease enzymes cut the peptide bonds in the thyroglobulin to produce much smaller thyroid hormones T3 and T4. So if we take a quick look at the structural formulas for the different thyroid hormones, T3, or triiodothyronin, makes up slightly less than 10% of all thyroid hormone produced by the thyroid, but it is by far the most biogenically active of the thyroid hormones. About 90% of the thyroid hormone that is made directly by the thyroid is T4, or thyroxine. It is not nearly as active as T3, but once T4 is exported into the bloodstream, enzymes throughout the body will remove one of those iodines and convert it to T3, in which it is much more active. So if you're keeping up so far, T3 and T4, you may be noticing T3 contains 3 iodine atoms and T4 contains 4. So if enzymes throughout the body want to convert T4 into T3, all they have to do is remove this iodine atom right here. Now, we will go ahead and mention reverse T3, which makes up less than 1% of all thyroid hormone. It is totally inactive, and as we will see on the next slide, it is a product of enzymes throughout the body removing the incorrect iodine, which basically produces reverse T3, which again is not very active. So you can see that the idea that when you activate T4 and turn it into T3, the idea is that you would remove this iodine, but mistakenly, this iodine gets removed instead. So as I said, most thyroid hormone that is produced is T4. It doesn't have very much activity, but tissue enzymes throughout the body remove that one iodine that we saw before and convert it to T3 to drastically increase its activity. And then, as I also said, reverse T3 is totally inactive, and most of it is just mistakenly produced by enzymes throughout the body in an attempt to remove the right iodine, but they end up removing the wrong one. So any thyroid hormones that get produced prior to TSH exposure will just be stored up in the thyroid until TSH comes along. So we may have given the impression that thyroid hormone production doesn't actually get started until TSH exposure occurs, but there is some iodine import, there is some thyroid hormone production that occurs prior to TSH exposure. We're just going to store it up in the follicles until it is time to release that mature thyroid hormone by exocytosis once TSH binds to its receptor. So to illustrate this a little bit, we can see one of our follicles here, and then we can see the nearby blood supply here. TSH, which is coming from the anterior pituitary, will bind to receptors on the cells of these follicular cells here. That will trigger an increase in iodine transport across the membranes here. Oxidation of this iodine will produce I2, which is then incorporated into thyroglobulin via the organification reactions that we talked about. And then T3 and T4 will be exported into the bloodstream where it is picked up by thyroid binding globulin due to its hydrophobic nature. And then from there, this carrying molecule, or this carrier protein, will carry the T3 and T4 to various cells throughout the body that have thyroid hormone receptors. So the hypothalamus secretes TRH in response to low basal metabolic rate. So if you're kind of wondering, well, what's the whole purpose of thyroid hormone? Why do we need it? And under what conditions would we actually need to secrete it? Here's your answer right here. So let's repeat ourselves here. The hypothalamus secretes TRH in response to low basal metabolic rate. Basically, this is the rate of energy consumption by cells. A more practical way of thinking about this is the number of calories you burn every day by doing nothing. Okay? So for most people, your basal metabolic rate is going to be about 2,000 calories if you're a man and maybe a couple hundred less than that if you're a woman. So a low basal metabolic rate means that cells in the body will not have sufficient ATP production, and heat production will also be low. Recall that a lot of your body's natural heat production comes from all the various metabolic reactions that are happening throughout your body. So if someone's basal metabolic rate is unusually low, not only are they going to be feeling very lethargic and very deprived of energy, but they're also going to probably be feeling very cold as well. So these are the conditions, low basal metabolic rate, these are the conditions under which we need thyroid hormone to do what it does. Thyroid hormone in general increases basal metabolic rate and stimulates tissues throughout the body to start producing heat. So that should solve both of our issues there. So most tissues in the body do possess thyroid hormone receptors. So this is kind of similar to what we saw with growth hormone. It's not just one or two different types of cells, it's actually most cells throughout the body. So these receptors are located inside of these target cells, again, because T3 and T4 are hydrophobic hormones. So if we kind of take a look at what's going on here, T3, which is being carried by thyroid binding globulin, will be released into its target cell where it will bind to a receptor that is located on a mitochondrion. This will stimulate the mitochondria to ramp up their metabolic activities of producing ATP through cellular respiration. And separately, we will also see increased transcription and translation of metabolic enzyme genes to help speed up this process of producing ATP and also radiating heat outward. So the net effect here is that this will increase basal metabolic rate, increase body temperature, and also increase heart rate and breathing rate in an attempt to rid the body of any excess carbon dioxide that is being produced because of increased flux through the mitochondria. So let's also talk about some thyroid pathologies. Because the effects of thyroid hormone activity are so cut and dry, when we talk about having too much thyroid hormone, which we call hyperthyroidism, or too little thyroid hormone, which is called hypothyroidism, the symptoms that we see of this are actually pretty easy to predict. So if you look under hyperthyroidism, you can see that a person who has too much thyroid hormone is going to be feeling hot all the time. They're going to have an increased appetite and they'll be losing weight even though they're not trying to. Their pulse and breathing rate will be high. Their energy levels will be high. And then if we compare that to someone who has hypothyroidism, they're going to be experiencing exactly the opposite. They will be feeling cold all the time. They won't be eating very much, but in spite of that, they'll be gaining weight. Their pulse and breathing rate will be very high, and then their energy levels will be rather low. Their pulse and breathing rate will be very low, and their energy levels will be very low. Another common pathology associated with the thyroid is called a goiter. This is an enlarged thyroid gland caused by excessive production of TSH, which is often caused by iodine insufficiency. So I mentioned that iodine has to be obtained through the diet. We don't need very much of it, but if you don't get enough of it, leave it like that for too long, and your thyroid will swell up like a melon, as you see here. So the idea behind how a goiter comes to be is that even if all the involved glands, the hypothalamus, the anterior pituitary, and the thyroid, are healthy and functional, a lack of iodine means that no thyroid hormone can be produced. So this dates back to our discussion on hypertrophy and atrophy. So let's take a look at how this comes to be. So if the amount of iodine obtained in the diet is adequate, then thyroid hormone production should be normal. Hypothalamus produces TRH. This causes the anterior pituitary to produce TSH. The thyroid, if iodine is obtained in sufficient quantities, should produce T3 and T4. However, if we operate under the assumption that there is not enough iodine, then this is going to drastically reduce the amount of T3 and T4 that can be produced, if any can be produced at all. So the idea here is that the thyroid is being told by the anterior pituitary to make T3 and T4, but in spite of receiving that message in the form of TSH, the thyroid cannot produce it because it does not have the raw material it needs to do so. So when thyroid hormone levels are high, this typically triggers negative feedback to shut down the production of TRH and TSH. Well, in this case, we're going to see the opposite. Because T3 and T4 levels are so low, that removes the negative feedback and it causes TRH and TSH to get much higher. So low thyroid hormone levels causes TRH and TSH levels to continue to rise. So think of this from the perspective of the anterior pituitary. It is sending TSH to the thyroid. It is telling the thyroid, hey, you need to be making thyroid hormone. So if the thyroid doesn't produce the thyroid hormone, the anterior pituitary is going to assume that, well, the thyroid's not listening to me. Well, I better tell it again, except I better tell it louder this time. So from the anterior pituitary's perspective, it's thinking, well, if I just bombard it with even more TSH, maybe it'll listen to me next time. So the thyroid is now being bombarded with TSH despite its inability to make thyroid hormone because of the low levels of iodide. So the thyroid is now overstimulated with TSH, and it is going to grow as a result. Again, that is hypertrophy, and that is how you end up with a goiter. So some final thoughts and tidbits on the thyroid before we wrap up this video. Thyroid hormone is an important component of fetal and childhood tissue development, most particularly neurological development. We mentioned that briefly before when we talked about it having some permissive effects with testosterone and estrogen. Speaking of which, thyroid hormone shows synergism and permissiveness with a number of reproductive hormones in adult development as well. Hypothyroidism levels of testosterone and estrogen as well. Okay, that's going to do it for this video. Here is a list of vocabulary terms you might want to be aware of. And for checking your understanding, number 1, what class of hormones do TRH, TSH, and thyroid hormone fall into? Number 2, how is thyroid hormone made? Number 3, what systemic effects does thyroid hormone have on the body? And finally, number 4, what are the characteristics of hyperthyroidism and hypothyroidism? Okay, that's going to do it for this video. If you have any questions, go ahead and drop them in the comments section, and I will see you next time. So long.